Italian's not here. Well, thank you. I'm very happy to be here in India, especially for this celebration of Kali and Sina. And I wanted to give an overview of some work I've been involved with and also work of other people related to it, of a topic of interest to me, which is local eigenvalue statistics for random Schrodinger operators. So I'm going to begin with a overview, since many of you might not have worked in random Schrodinger operators. I talk a little bit from a different perspective. I'm not going to talk too much about spectral methods per se, but I'm going to talk about some random processes that arrive naturally. Why the feedback is so up? That arrive. I guess I'm magnetic. How about that? So I can talk about some introduction of basic facts. The density of states is one of the key objects, and I'll give an overview of that. And then what I'd really like to be able to share is two models where one has a pretty good idea of a change, a particular transition in the behavior of local eigenvalue statistics. And one of the models is so-called scale disorder model, which is a one-dimensional sort of toy model, but you can do a lot of explicit calculations. And the second model is a model which sits at another extreme, sort of the random band matrix model, once again in which you can see a desired change, a transition in the local eigenvalue statistics. Okay, so let me get started and talk about random Schrodinger operators. Schrodinger operators are simple linear operators on a Hilbert space, and I'll always write them as a sum of two terms. H0, and this is not working too well, but H0 is a background potential. Take it just to be the Laplacian on, let's say, RD, or the finite difference Laplacian if you're working on the square lattice ZD. And the randomness enters in a multiplicative function V sub omega. So omega sort of tells you the interaction strength of a particle moving through this disordered media. And there are two models which one can keep in mind, and I'm not quite sure how to minimize that feedback. Can you turn it down just how's that? But now you can't hear me. I'll try to put it up here. Okay, so maybe that'll be better. So you can either work on the Hilbert space of square summable sequences on ZD or on functions on RD, and I'll go back and forth between them. Basically, the ideas are the same. There are a lot of technical differences, which I won't go into. So H0 is a fixed background self-adjoint operator, as I said. Just think of it as the Laplacian, the sum of the squares, the second derivatives on RD. The random potential might be new to some of you. So if you're working on little L2 of ZD, then what you do is you simply take the function on the lattice at a point k, you multiply by a random variable omega sub k. If you're on the continuum, of course, the evaluation at a point on functions in L2 isn't very well defined. So what you have to do is, here are the random variables omega k. Instead of the projection on a particular point, a lattice point, let's say k inside of ZD, you smear it out a little bit, and occasionally we'll see this function u. So you just take the origin and you take a smooth bump function, looks something like that, non-negative, and so that's the strength with which, let's say, a quantum particle interacts with this surrounding located at the point k. So you just translate to this point k. And then the strength of that is given by omega, which fluctuates. So the family for each point in ZD, omega sub k, is a family of random variables. For simplicity, I'll take them to be independent, identically distributed. I'll make some comment about the distribution. Usually we're going to treat the case for simplicity that these are distributed with a measure that's AC with respect to Lebesgue. So there is a density, let's say, that's smooth and has compact support. Okay, so those are the two components of this linear operator, the Schrodinger operator. And what you should think about this is actually a family, of course, of self-adjoint operators, because as omega varies, the potential varies, so you get a whole family of operators. And was long ago in the 70s realized that you can't fix a configuration of these potentials. These are bumps, right, located in the lattice in space. But what you want to do is sort of treat the ensemble of all these omega. And the trick to do that is to realize that if you were to conjugate this self-adjoint operator by the translation group, then you have a miraculous covariance property. Because the random variables are IID, a translation in space from one lattice point to the next gives rise to a translation in the configuration. That is to say, there's an action on the probability space, and because they're IID, you have the same, once you do a translation in space, the operator belongs to the same family simply with all the random variables being likewise translated. And that's an ergodic action on the probability space with the product measure. And consequently, you can talk about things that are almost sure. And an important thing to realize here is that the spectrum, which fluctuates as you change the configurations omega, is stable if you look at almost all configurations. So there is a fixed set, sigma I'll use in the talk, which is a closed subset of the real line, such that with probability 1, the spectrum of these self-adjoint operators is that fixed set, right? So then we can talk about the spectrum with probability 1. This is called the deterministic spectrum of this system. I just repeated on this slide what I said. You have independent, identically distributed random variables. Occasionally, I'll use this fact rho for the probability measure for the random variables. Of course, you only need it at one point because they're IID. Okay? So let's go on and talk about this. Of course, if I'm working on L2 of RD, this is a self-adjoint operator. It's unbounded. It has, in general, a very complicated spectrum. But what I want to do, first of all, is restrict the operator to a finite region in space, because then the operator has purely discrete spectrum, only eigenvalues. And it's those eigenvalues I want to study. I want to introduce a statistic associated with those eigenvalues, and then look at, for appropriate scaling, how this behaves as the size of this box where I restrict the system goes to infinity. So just some notation. So lambda sub L is a cube of side length capital L, and H super lambda sub omega is simply the restriction of the operator to that cube, right? And you put this appropriate boundary condition, so it's a self-adjoint operator. The spectrum then is just discrete. So I'll write the eigenvalues as E sub j super lambda of omega, and there are n eigenvalues for this restricted operator. One of the first places we see the difference between the continuum model and the lattice model, of course, is that on the lattice model, the number of eigenvalues is exactly the size of the box, the number of lattice points. And it's just a matrix, right? If you wish, you can just think about this as a big size of lambda by size of lambda matrix. In Rn, of course, if you restrict even just the Laplacian to a box, you have an infinite number of eigenvalues. Okay, so that's just one difference to keep in mind. The density of states, in some sense, is a normalized counting of the number of eigenvalues. So if you fix an interval of energy, let's say I, which of course is a subset of the real line, and denote by E sub the operator of I, the spectral projector for that self-adjoint operator in I, that the trace of that is just the number of eigenvalues of that operator in the interval I. I want to regularize that by taking the expectation with respect to the finitely many random variables for the system in the box. So I take the expectation of the number of eigenvalues, divide by the volume of the box. That's the normalized number of eigenvalues per unit volume for that operator. I'll write that as n sub lambda of I. That actually has a limit as the volume goes to infinity. Again, because of the ergodicity, underlying ergodicity of the system. And that limit is called the density of states measure. And I write that down below. So n of I is just the integral of a measure, the density of states measure. And it's this quantity will show up in my later discussions about local eigenvalue statistics. So we have the system in a box, have a family of eigenvalues. We looked at the counting function properly normalized by the box and the local density of states, which is little n sub lambda. And then when you take the volume of that box to infinity, you have the density of states measure for the infinite volume system. Just one other comment about this measure of density of states measure, the integral of that gives you the distribution function, which is called the integrated density of states. And then when the derivative of that exists in appropriate sense, that gives rise to something called the density of states function. And for many of the models I'm talking about, that function exists at least locally as a locally bounded or locally L1 function. When the single site density rho is not going to play much of a role here, so I'll drop that from the notation. Okay, so let me introduce the main topic of my talk, that is the local eigenvalue statistics. Now that we have eigenvalues and we have some way of counting them, what we do is, again, here's the listing of the local eigenvalues. And what we do is the following. We'd like to fix a number E0. So I remind you that from the point of view of the spectrum of the operator of H omega, there's this subset sigma, which is the almost sure spectrum. So let me just, for example, write it down here as if we're on the lattice model. We want to fix some E0, which belongs to sigma, and we want to ask for the finite volume system, look at the eigenvalues that are nearby E0. Well, I'll show you later on that the average spacing between these eigenvalues is 1 over the volume of the system. So I want to rescale the spacing of the eigenvalues near 0 by the volume. So this quantity, if I look at this process, that is to say, this is a family of rescaled random variables, and I consider the process that puts a delta function at each of those points, so that gives me a random measure. I want to ask that random measure, how does it behave as I let lambda become very large? So when I talk about the local eigenvalue statistics, I mean the behavior of this family of rescaled eigenvalues about some fixed point E0, and I'll write that as psi super lambda for the finite box sub omega. This is, of course, a point process, a random point process on the real line. It's measuring the average rescaled eigenvalue spacing around this fixed energy E0. So then there are a number of questions about this. First of all, does it converge as I take the volume to infinity, right? And of course, then can I characterize the limiting point process? So this has been a question in the field since about the 80s, when Molchanov did some work on one-dimensional models. It really got a boost in the late 90s when Minami proved some strong results I'll mention in the next page. And it's a continuing interest of people working in random Schrodinger operators. So the first question does have an answer that usually you can prove some weak convergence of these finite volume local eigenvalue statistics, these finite volume point processes, as lambda goes to infinity. You have some weak convergence. You might not get a unique or be able to prove that the limiting process is unique. It depends on the situation. How do you characterize the limiting point process? Well, it depends upon how you choose this initial point E0, where you're looking at the local eigenvalue spacing, and it also depends on the spatial dimension D. So let me give a little overview of some conjectures about the behavior of the local eigenvalue statistics. To do that, I'll just sort of argue a little bit heuristically. Let me go over here and draw a picture of a one-dimensional picture. Lambda sub L looks something like that. If I have an eigenfunction, looks sort of like that, let's say. Of course, this is just a picture of it. We talk about the localization length of this eigenfunction, which is basically the region where most of the mass of the eigenfunction lives. So this gamma sub L is sort of what I talk about, the localization length. It's where most of the eigenfunction lives. And in considering what happens as L, the size goes to infinity, I want to look at the ratio of the localization length to the size of the sample, to the size of the box. And there are two different possibilities as L gets large. Either that ratio of localization length of the eigenfunction to L goes to 0. That means that I've taken a box size that has perhaps many of these eigenfunctions inside. So I really see that the eigenfunction is living inside on the scale L. And in that particular limit where the ratio goes to 0, physicists believe that the limiting point process that I described concerning the eigenvalues is in fact a Poisson point process. And I'll give you some other ideas of how that can be turned into a mathematical proof a little bit later on. On the other hand, if you look at another picture on scale L, and suppose that the eigenfunctions are sort of very large over the scale length L, so that when I take the ratio of the localization length to the size of the box as L goes to infinity, that stays positive or even diverges. So what that means is that somehow if I'm sitting at this scale, capital L, I just sort of see an extended state of the system. The eigenvector or the eigenfunction is basically flat across that scale size. In that particular situation, number 2 here, so if my E naught is in a region for which this gamma localization length over L stays large, stays non-zero as L goes to infinity, physicists had believed that you get the following, that the limiting point process is the same as the limiting point process for coming from random matrix theory for the Gaussian orthogonal ensemble. So in some sense, when studying random Schrodinger operators, one would hope that, or one believes that depending upon where you choose the centering point energy E0, you may, if you're in the so-called localization regime, point number 1 here, end up with a limiting point process that's Poisson. And if you're in another so-called, let's call it delocalization regime, where point 2 holds, you end up with something that is similar to random matrix theory, the GOE or the Gaussian orthogonal ensemble. That is the transition I was referring to earlier on, that depending upon where E0 is for the spectrum sigma of the model, you may be in the delocalized regime or in the localized regime. So one of the goals of this sort of quest is to prove that for reasonable models of Schrodinger operators with random potentials, you actually have this transition. Now, how does the dimension enter in? Because I was talking about one dimension here, sort of. The dimension enters in because it is known that for one-dimensional disordered Schrodinger operators, your E0, no matter where you pick it, you're always in this localized regime. Okay? In 2 dimensions, physicists are not sure. In 3 dimensions, the picture that I discussed here should hold true. So that if I take a 3-dimensional random Schrodinger operator, and I should be able to find regions where the limiting point process is Poisson and where the limiting point process is given by the GOE. That is a goal which has not been achieved yet, let's say for the 3-dimensional random Schrodinger operators that I sketched. And so when I talk about some models, I'll talk about some toy models where you can actually see it. So concerning a little bit more about this previous conjecture, because I wanted to show you some pictures, this limiting point process, the LES that I described, it's not too physical about how these eigenvalues behave, what it says about the behavior of eigenvalues. If I introduce another statistic, which is the level spacing distribution, I'll show you some very nice pictures that are easily generated. That is to say, suppose I look at the eigenvalues and their differences. So suppose I look at Ej, lambda of omega, and I order them in increasing size, j plus 1, so forth. And I look at the difference between 2 successive eigenvalues. So this level spacing distribution function says I look at the difference between 2 successive eigenvalues and I rescale, as I did before, according to the volume. You can also rescale according to the density of states function. And I ask basically, out of all the eigenvalues in a fixed interval I take the ratio of the number of successive pairs that are bigger than some number x and divide by the total number of eigenvalues. So this is the level spacing distribution function. If you take the limit to infinity, it's known that the limit exists, that's LSD of x, the level spacing distribution. And once again, the behavior of the level spacing distribution, we'll see, depends upon whether E0 is in this localized or delocalized regime. And the conjecture, which I stated in words, actually is this conjecture in pictures. So if you're in the localization regime, the density of this level spacing distribution function should be an exponentially decaying function. So the density P of S is e to the minus S. So here I'm graphing the spacing between successive eigenvalues. It's just a histogram in the number. I didn't make a picture of the Poisson. It would just be an exponentially decaying function. On the other hand, if you're in the delocalized regime, that is where random matrix theory is supposed to control the level, the LES, and also the level spacing distribution, what was known from the time of Wigner, the so-called Wigner surmise, is that approximately the density of the level spacing distribution is completely different. It goes like S to the power 1 in the GOE case as S goes to 0, and then it decays like a Gaussian. So these bumps are signatures of that delocalized regime. And so one of the great goals would be to show that for random Schrodinger operators, if you pick E0 inappropriately, that in fact your level spacing distribution looks something like that. Now notice here it says that eigenvalues don't like to get too close. It says the number of eigenvalues properly rescaled, right, the difference, EJ plus 1 minus EJ, there are very few of them. That's interpreted as level repulsion or repulsion of eigenvalues, whereas for the Poisson case, it doesn't really matter. It's exponentially decaying. They can be close together. They can be far apart. In other words, they don't see each other. So in the localized regime, the idea is because the eigenfunctions are very well localized in some region, the eigenvalues basically don't feel each other. The eigenfunctions behave like they're independent in some sense of the other random variables far away, whereas in the delocalized regime, you have level repulsion. The eigenvalues don't like to be close together. And we'll see a little bit more of that quantitatively as I move on. Okay, just a little note about some of the technical work behind what I just described. As I mentioned, in 1996, Minami looked at the local eigenvalue statistics in the localized regime and proved for the lattice models that, in fact, it's given by a Poisson distribution. And this density of states function you saw before at the energy E0 is the intensity measure, gives the intensity measure of the limiting Poisson statistics. This was refined in a very beautiful paper by Germanet and Klopp a number of years later. They reproved the Minami result using a different sort of interpretation of the localization regime that I'll talk about. And they also established that the level spacing density is an exponentially decaying function, as I showed you in the last graph. A few years later, my colleague Krishna and I looked at this question. If you have the local eigenvalue statistics, is there some limit point, and what is the nature of the limit points? And in the localization regime, we found that you do always have weak limit points, and it's given by not necessarily a Poisson process, but something somewhat more complicated called a compound Poisson process. So that was an answer to one of the questions I posed earlier. In a model in 1, 2, and 3 dimensions, slightly different, where you add delta interactions with Krishna and with our colleague Werner Kirsch, we in fact proved again in the localization regime that you get the local eigenvalue statistics being Poissonian. The goal in that result, and the next result I want to mention, is that Minami proved his result on the lattice model on L2 of ZD. There's some technical correlation results which had eluded all proofs for many, many years, which I'll show a simple example of in a few minutes. So the so-called Minami estimate now that had not been proved on L2 of RD. And consequently, this result was one of the first where you could establish local eigenvalue statistics in the continuum, even though it's not the model I introduced earlier on. Recently, Dietlein and Elgart were able to prove one of these second-order correlation results in the continuum, and consequently, you could prove local eigenvalue statistics at the bottom of this deterministic spectrum sigma, where localization occurs. So that's sort of a summary of those results. So for the rest of my talk, I want to give two very simple models And again, they're a little bit far from proving the result in 3 dimensions for random Schrodinger operators. However, the models give us a lot of insight that transitions in the local eigenvalue statistics actually can occur. The first model that I'll talk about is so-called the scaled disorder model. And it's kind of nice and allows you to see exactly those 2 regimes that I talked about earlier in the general conjecture, because you can compute the localization length and you know the size of the box. So this particular model is characterized by the following. You fix n and you work on an interval of length size 2n, so basically of n, and you scale the interaction term, the strength of the disorder, with n. So the scaled disorder says instead of just having the omega j, you scale that by 1 over n to a power alpha. And I'm going to take alpha between 0 and 1. Now for this type of model, so I'm just restricting the length, capital L before is now 2n. This is just the finite difference Laplacian. Doesn't really matter, a deterministic self-adjoint matrix. For this particular model, what's interesting is that the localization length is 1 over the square of the strength of the disorder. So the localization length is n to the 2 alpha divided by sigma squared. Sigma you might as well take equal to 1 from now on. So the ratio that I spoke about, gamma n to n, the sample size, scales like n to the 2 alpha minus 1. Right? So remember, we wanted to see when the size of the sample goes to infinity, what happens to this ratio. And you immediately see that there is a critical alpha, and you have 2 regimes. So when alpha is between 0 and 1/2, the n to the 2 alpha minus 1 is decaying. So in that case, the ratio goes to 0, and we would expect to get the Poisson point process as the limit. Alpha equal to 1/2 is critical, because you have neither have decay nor bounded from below. And finally, when alpha is bigger than 1/2, you're in this second part of the conjecture where you stay bounded away from 0. In fact, it diverges. And so the conjecture, again, was that you get Poisson statistics, critical. Since this is a one-dimensional model, you don't get the so-called GOE statistics, but you get something which is somewhat similar. It's named, Barry Simon, I believe, in the audience named this the clock model for another matrix model, quite interesting that I won't talk about. And what that exhibits, though, is rigid repulsion of the eigenvalues. Okay? So you have eigenvalues acting somewhat independently, eigenvalues really not liking their next eigenvalue next to them, and you have rigid repulsion. And that's similar to the GOE statistics. So those are the conjectures for this particular model. As you see, it works out. And just to mention, if you have no interaction at all, then the Laplacian statistics are also like the clock statistics. So that is the delocalized phase. So there have been various, let me just go back for a second. There have been various results. Krzyzewski, Valko, and Virag did a beautiful analysis using stochastic differential equations for the alpha equal to 1/2 and studied the special process that occurs there. I refer you to their paper. And then Kotani and Nakano, and also working with Frederick Klopp, we looked at the other 2 regimes. And I want to just say a few words about, again, how could you get the limiting eigenvalue statistics to be Poissonian in that first regime? Well, the idea sort of was encapsulated in the picture that I erased, that if in this regime from minus n to n, your eigenfunctions are sort of well localized inside, right? And so what you want to do is to take this large region and cut it up into smaller regions, and then look at the structure, the Hamiltonian for each smaller region. And the idea is that really if you see the ratio of the localization length to the region of the size is very, very small, then somehow for each eigenvalue on the large scale n, you should be able to find a small region such that the Hamiltonian on this small region has an eigenvalue that's very close to the given eigenvalue at scale n. Consequently, all the eigenvalues in my interval of energy on the scale n will correspond to eigenvalues on smaller scales n prime. And those small scale Hamiltonians are independent. So the eigenvalues are independent. So the moral of the story is in the localization regime, the eigenvalues on scale n of the Hamiltonian behave like independent random variables. That's the clue to the idea that the limiting statistic should be Poissonian, as I show you. So just technically what you do in this regime, the localization regime, is that you pick another scale alpha prime. So remember, the localization length is n to the 2 alpha, so that on the smaller scale, you see some of the localized eigenfunctions. So again, you're in a localized regime on the smaller scale. So these lambda n prime are the smaller boxes, which still contain a number of eigenfunctions. And then with a good probability, the eigenvalue in an energy interval at scale n should be close to an eigenvalue on the smaller scale. And the smaller scale Hamiltonians are independent, so basically the eigenvalues behave more or less like independent random variables. Okay, so to make that, just to give you a technical idea, what you introduce is a notion of a center of localization for an eigenfunction. It's basically the point where the eigenfunction obtains in absolute value its maximum. And what you can actually prove is that the center of localization for the Hamiltonian on the big scale in a given interval always lives in one small scale interval. And there's at most one center of localization at the small scale. So consequently, you can do this division of the eigenvalues into eigenvalues of Hamiltonians on the small scale. And in fact, as I said, that if a small region contains a center of localization on the big scale, then the Hamiltonian on the small scale has a nearby eigenvalue in pretty much the same region of energy. And again, all this is done with a good probability, 1 minus n to a power. So as n goes to infinity, this holds almost surely. So this is the basic idea again. The eigenvalues on the smaller scale for different j are independent. And an eigenvalue on the bigger scale is very, very well approximated by an eigenvalue on the smaller scale. Okay, so with a good probability, all the eigenvalues look like eigenvalues on the small scale Hamiltonian. And why is that good? Well, because you go back to an old idea of how you use a Bernoulli distribution to approximate a Poisson distribution. So let me just review that for a moment. If you have a family of independent Bernoulli random variables, so the probability of it being 1 is some number Pn. I have n of them, and of course being 0 is 1 minus Pn. Then suppose you want to ask, how do I choose k points from 1 to n so that the random variable at each of those k points is equal to 1? Well, that's just a Bernoulli distribution. So if you know, finally, that the limit of the product of the probability at scale n times n is non-zero, let's say lambda, then in fact this Bernoulli distribution converges to a Poisson distribution. So the idea is in a localization regime, the eigenvalues on scale n are the eigenvalues of the Hamiltonians on smaller scales, which are independent. And how do you get the Bernoulli random variable? Well, you just define a Bernoulli random variable the following way. So it's 1 if the local Hamiltonian has an eigenvalue in the energy interval and 0 otherwise. So now I have a family of independent Bernoulli random variables. I can go back to the previous slide and compute this probability. And actually, the main technical result that remains to be shown is to figure out the probability. This is my P sub capital N times the number of sites that I have, that the limit as little n goes to infinity has to converge to something which on the previous slide I called lambda here. Okay, and that takes a little bit of work. In fact, it converges to the density of states at energy 0. And so consequently, applying this Poisson limit theorem, you get Poisson statistics with that measure. Okay, so localization means eigenvalues behave. They don't care about the other nearby eigenvalues that behave independently. you get a family of independent Bernoulli random variables, and you get Poisson statistics. So it's basically the idea. Sorry, let me.
This is for the case with the coupling constants are decaying?
Yeah, this is the case where the coupling constants are scaled, right? So it's omega j divided by n to the power alpha. So they're decaying, but they're decaying constantly across scale length n, right? You can also do it for decaying, right? No. What's that?
For the decaying case, you don't know what density of states is.
Well, in all these cases, you can, in this case, I noted, since you raised the question, n sub 0 is the density of states function for the Laplacian, right? Because the potential disappears, right? Right. So we can talk about the other case later on. Okay, so that was what I wanted to say about the scale disorder model. Let me finish by talking a little bit pictorially about the random matrix model. So what's the random matrix model? So, well, you take a matrix, big matrix, let's say, of side length n, and I want it to be real and symmetric, and so every entry in this n by n matrix is a random variable. And let's say take them, for simplicity, the original model, let's take them to be Gaussian distributed. That model is the model that Wegener studied back in the 50s, and in fact, this is the classical Gaussian orthogonal ensemble. What I'm sort of interested in is, instead of taking this large matrix, let's take a banded matrix where you only have random variables in a band. So when the size of the band is the same as the size of the system, that's a full random matrix. If you think for a few minutes when the size of the band gets very small, in fact, our Schrodinger operator is a Jacobi matrix on the lattice in the previous example. It has diagonal disorder, and then the free Laplacian gives some off-diagonal terms. So the random band matrix model is viewed by some people as an interpolation between the random Schrodinger model on a lattice and the Wegener Gaussian orthogonal ensemble. And so one had hoped that in an appropriate regime, you could interpolate between random Schrodinger and the Wegener ensembles, like GOE. So the random band matrix has matrix elements that are IID, let's say Gaussian random variables. You scale by the width W of the matrix so that the variance of these random variables is 1 over W. Okay? And let's take n by n matrices. So a very simple model, n is fixed. Actually, for counting, I'm doing 2n plus 1, so you have n on each side. And so the width, I'll write in a moment, is 2l plus 1. Okay? Again, you can take many different types of distributions. Just think of Gaussian mean 0 and variance 1. So the variance of the scaled random variable is 1 over W. And as I said, there are two extremes. Actually, in the case that W is equal to 3, where I'm just sort of saying looks like a random Schrodinger operator on the lattice in one dimension, there you're supposed to have complete localization. And on the other hand, when the width is 2n plus 1, the size of the system, then you're in the delocalized regime. That's like number 2 in the conjectures that I mentioned a little bit earlier. So what are the open conjectures for random matrix, band matrix models? So I have a random band matrix model, and I take the width to scale like n to the power alpha. Right? So the scaling power alpha, again, is going to be between 0 and 1. So the conjecture is that if alpha is less than a half, greater than or equal to 0, so that's near the localized Schrodinger operator regime, which is alpha equal to 0, then the limiting point process should be Poisson. Just as we saw a little bit earlier in the beginning, the eigenvectors are exponentially localized, and the spectrum is almost surely pure point, are some conjectures. On the other hand, conjecture number 2 says now for alpha bigger than or equal to a half, the limiting point process should be like the GOE, just as we saw earlier, and the eigenvectors are spatially extended. So the model, as model number 1, exhibits should exhibit a localization, delocalization transition. So what are some results? Well, it's rather interesting, especially for someone coming from Schrodinger operator theory, that for this model, the delocalized regime is very well understood, or at least better understood than the localized regime. Usually for Schrodinger operators, it's the opposite. So one of the main results to date by Bourgade, Yao, and Yin is that if the width is at least n to the power 3/2, so 3/2 is still a bit far from 1/2.
You wrote 3/4. You mean 3/4 or 3/2?
No, that was a mental leap. 3/4, sorry. 3/2 would be bigger than Wigner, right. So 3/4, which is bigger than 1/2. Then in fact, they have proved that the eigenvectors are extended, right? So that there's weight basically on all the sites in the lattice from -n to n. So you have extended states with a very good probability. And in fact, that the limiting density of states for this model satisfies what's called the semicircle law, which I've written down there for the integrated density of states with a good probability. And what is really neat for us is that the local eigenvalue statistics are Gaussian, given by the Gaussian orthogonal ensemble, again up to good probability, that the k-point correlation functions for the eigenvalues converge to those for the GOE. So that's a really beautiful result. Of course, a lot of work still needs to be done to change the exponent down to 1/2, as is anticipated and given in the conjecture. On the other side, on the localization side for alpha less than 1/2, right? So this is basically narrow band, alpha less than 1/2. Much less is known. There are some estimates for n being finite that involve the correlations of the eigenvalues, so-called Wigner and Minami estimate that I mentioned a little bit earlier, and also some localization bounds. But to date, the best results are known only for alpha less than 1/7. And in fact, the Poisson statistics are not known. And that's one of the open problems when alpha is strictly bigger than 0 and less than 1/7. We have localization results. So let me just finish by giving you some ideas. Remember earlier I introduced the spectral projectors and the trace. This is just counting up the number of eigenvalues of H in the interval I. So the so-called Wigner estimate, a first correlation estimate for these eigenvalues, says that this expectation is bounded above by the size of the system and the length of the energy interval I. That's the estimate that shows that the average eigenvalue spacing goes like 1 over the size of the system that I used earlier for scaling in the local eigenvalue statistics. A more interesting result that I mentioned earlier, the Minami estimate, is basically a second order correlator for the eigenvalues. And basically, it's bounded above by the square of the upper bound of the 1 of the first correlation function for the eigenvalues. So those have been proved by several different people. I'll mention at the end. This means the probability of having 2 eigenvalues near each other in an interval goes like the square of the size of the interval and the size of the system. Now, what problem that I've been working on with the student Ben Brody and also discussing with Krishna is in the localization regime, right? How can you use these estimates in order to prove Poisson statistics for the limiting eigenvalue process? Let me just briefly go on since we're just about out of time. There are other estimates a priori bounds on the matrix element of the resolvent, which one needs to prove for these models, where H omega is the random band matrix that I introduced. And most importantly, in this side, when alpha is less than 1/2, you have localization bounds. So just let me point out, this says that if you take the matrix element of the resolvent of the random band matrix between 2 different states, then in fact, the expected value of a small moment decays exponentially. All right? And that's a signature of localization. That's true for the random Schrodinger operators in the beginning that I talked about in the localization regime. And this proof has been extended by my student and I from Schenker's original bound so that we can use it to get to the local eigenvalue statistics. Now, I mentioned if you want to prove Poisson point process, one of the key steps is to identify, basically going back to the Poisson limit theorem, this product of the size of the system times the probability of the Bernoulli random variable being equal to 1, that a local system has an eigenvalue in a given interval. And again, that's very important. In fact, that's a missing link. Once you have the localization bounds, you need to prove something like this theorem, that the local density of states function converges to the density of states function when n is infinite. Now, in this particular case, I'm going to take the width to be independent of n, so that when n becomes infinite, this is just an infinite by infinite matrix, so this quantity here is well defined. And once you have that estimate, then in fact, looking at the rescaled local eigenvalue statistics, you can prove the probability that the trace of this local spectral projector, or sorry, that the, I should have put the expectation here, I'm sorry, the limit as n goes to infinity is in fact this quantity which is the intensity of the limiting point process. And so consequently, the local eigenvalue statistics for the fixed width random band matrices, as I described, is a Poisson point process exactly with that intensity. And so one of the open problems in this field is to extend from basically alpha equal to 0, which is the end of the localization regime, further into towards 1/2 as expected. That localization bound at the moment is known only up to a 7th. So to get the Poisson statistics, what we're attempting to do is to allow the bandwidth to grow up to alpha less than 1/7 so that we have local eigenvalue statistics. So that concludes my talk. I just wanted to give you an idea of random Schrodinger operators, some interesting and new results on transitions in the local eigenvalue statistics, a flavor for what is localization, what's expected to be delocalization. The big conjecture is, let's say, in dimension 3, for those original Schrodinger operator models, you have a transition from localization to delocalization. That we don't know how to prove yet, but there are these two models, the scale disorder model and the random band matrix model, which gives some realistic justification for trying to pursue those other two conjectures. So thank you very much.
Then we have to eat lunch.